Hello everyone, welcome to this video on vector calculus. This video primarily concerns about what is meant by a scalar potential of an irrotational vector. So we have already seen that by an irrotational vector we mean that the curl of the vector is going to be equal to 0. So how to define curl? Curl is nothing but del cross of f vector. If f is going to be any vector which has been given to us, then when we compute del cross f and if it turns out to be equal to 0, then we call it to be an irrotational vector. Now what is the scalar potential of an irrotational vector? Okay, we will move with the video. We say that if f is going to be irrotational, then it can be expressed as the gradient of a scalar point function. So f is going to be irrotational. What do we mean by this is when the curl of your f vector. What is the curl of the f vector? Del cross product with f vector. If this del cross product with f vector becomes equal to 0, then this f vector is called by the name irrotational vector. Irrotational vector. Let this f vector be of the format, say f1 times of I plus f2 times of j plus f3 times of k. Now what do we mean by del cross product with f? We know that the vector differential operator del is defined as I dou by dou x plus j dou by dou y plus k dou by dou z. So if we want the cross product, so the cross product is now taken by the 3 cross 3 determinant. So how to estimate it? You have the 3 cross 3 determinant where the first component is going to be equal to your I, j and k. So you have I, j, k vector. Next, from the del you take the I component. What is the I component over here? Dou by dou x. What is the j component of your del? Dou by dou y. And what is going to be the k component of your del? It is going to be dou by dou z. And now coming to the second f. This f vector has f1i, f2j, f3k. What is going to be the I component? I component is nothing but my f1. What is the j component? J component is your f2. And what about the k component? It is nothing but my f3. If I am going to compute this 3 cross 3 determinant and find that this is going to turn out as 0, then you call this vector f to be an irrotational vector. Irrotational vector. Why we are giving this name? This because del cross f represents curl. Curl means the habit or the potential to rotate about a given point. If it is not going to rotate, then what will happen? Then the cross product will become 0. So the non-rotation of it now gives the name to the f vector as irrotational vector. Now moving on with the expression. Now what they are saying is if f vector is going to be irrotational, then you can express it as the gradient of a scalar point function. Now scalar point function, this is going to be a scalar function. Say suppose del is going to be the scalar point function for us. Now how to represent the gradient of a scalar point function? The gradient of it is given by this del operated on your scalar point function. Del is the operator which we have defined over here. So what will be our del phi? My del phi will be equal to I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. Now what they are saying, if f vector is irrotational, then what do they say is I can express this f vector as my del times phi. I can express my f vector as del times phi. So now this is going to be the concept which we are going to now solve using a problem. Now this function phi, which is going to be defined over here as a special name. This special name for this phi is referred as, this phi is referred by the name scalar potential of the vector f vector. Okay, scalar potential of your F vector. And this is going to be the task which are been now assigned for, or we are going to evaluate it for. Okay, we'll move on to apply this to a problem. Now the problem is, show that F vector is going to be given by y square plus 2xz square I plus 2xy minus z times j plus 2x square z minus y plus 2z times of k. We'll have to show that this F vector is irrotational and hence find the corresponding scalar potential of it. Okay, so we'll begin with the first task to prove that F vector is irrotational. So what is going to be the condition for us? Del cross product with F vector must be equal to 0. If I am able to show that, then I can show that F vector is going to be irrotational. Now let us move on to estimate what is going to be the cross product of it. So I have it to be equal to I component, a j component and a k component. Next, coming for my del, what is going to be my del? Del is going to be your operator I dou by dou x, j dou by dou y and k dou by dou z. Now what is the I component of it? This is going to be equal to dou by dou x. So under I, replace it as dou by dou x. Under j, write your j component. What is the j component over here? It is dou by dou y. And the last one is my k component, dou by dou z. Now coming to the second comp. What is this F vector? F vector also has an I, j and k component. What is the I component of it? This is now denoted by my F1, which is y square plus 2xz square. Now coming to the j component, I have it as 2xy minus z. Where is it? So it is attached along with the j over here. What is attached along with k? That becomes my k component. So it is 2x square z minus y plus 2z times of k. So now we are done. We will have to find the 3 cross 3 determinant of my component over here, and this we denote it by the name called as curl of F. If this curl becomes 0, then your F becomes irrotational. Now how to go about finding the 3 cross 3 determinant? The idea over here is hide the I, hide the j, I on top vertically as well as in the horizontal way, and then go for the cross multiplication. What is going to be the cross multiplication of the remaining quantity? This is going to be the cross multiplication of the remaining quantity. Okay, so we write this as I times dou by dou y of 2x square z minus y plus 2z minus dou by dou z of 2xy minus z. So this is my I component. Now coming to the j component. How to move on with the j component? What we'll have to do over here is hide this j vertically and hide the j horizontally. So whatever is going to be left out, that has to be done with the cross multiplication. What is the left out quantity? This with this. Now do the cross multiplication of these two quantity. So you will be having it as, second component always takes a negative sign, be careful about it, minus j times of dou by dou x of 2x square z minus y plus 2z minus dou by dou z of y square plus 2xz square. So we are now done with the j part. Now coming to the last component, which is k. How to go about the last component k? What we'll have to do over here, we will have to hide the value of k both vertically as well as in the horizontal way. If I am hiding it both vertically and horizontally, what is left out? This has to be cross multiplied now. So now moving on with the cross multiplication, I have this component as dou by dou x of, the component is 2xy minus z, dou by dou x of this, and dou by dou y of minus dou by dou y of the y square plus 2xz square. Now the next task is to just apply the partial fraction on it and then get your answer. So we will do the partial fraction of it. So it is I times of with respect to y, no y, so this becomes 0, no y, so this becomes 0, minus y becomes minus 1. Now with respect to z, this is no y, so becomes 0. Minus z will become minus 1. Minus of minus 1 will become plus 1. Minus j times of, moving to the second one. With respect to x, this component will give me x square on differentiation is 2x. Already there is a 2, so that makes it as 4xz. This doesn't contain x, this doesn't contain x. Again, this doesn't contain z, but this contains z. So z square on differentiation is going to be 2z, 2 2s are 4. So this makes with a minus sign outside, minus 4xz. And last with the k component, we have this to be equal to, with respect to x, there is no z, 2xy on differentiation partially gives me 2y. And y with respect to, this doesn't contain y, with respect to y, y square gives me 2y. So minus of 2y. Now we can notice that all of these components are going to be positive and negative of each other. And what happens? This gives me 0i plus 0j plus 0k. Hence you have it to be equal to a 0 vector. Hence what we have proved, our del cross f is going to be equal to 0. Hence we have del cross f as 0. So the vector is irrotational. And now comes the second part, which is finding its scalar potential. Now how to go about finding the scalar potential? I know that if it is going to be an irrotational vector, then my f vector can be expressed as del times phi. Now this f vector for me is given as y square plus 2xz square times of I plus 2xy minus z times of j plus 2x square z minus y plus 2z times of k. And what is this del phi? Del phi is nothing but equal to I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. Now right hand side also we have a vector and left hand side also we have a vector. When can we say that two vectors, a vector is equal to b vector? If their components in the respective directions of I, j and k are going to be the same, then we can say that the two vectors are equal. In which case, what do we have now is the I component. What is the I component of f? Y square plus 2xz square. This must be equal to the I component on my right hand side. What is the I component? Dou phi by dou x. Now comes the next quantity, equating your j component. What happens when we equate the j component in a similar manner? We have the comparison between the j component of f, which is going to be 2xy minus z, which is equal to the j component over here, dou phi by dou y. Now this is also done. So move on to evaluate with the third part. What is going to be the third part over here? The comparison with the k component. What is going to be the comparison of the k component? 2x square z minus y plus 2z is equal to, what is the k component over here? Dou phi by dou z. Our target is now to find this scalar potential phi. So what is my phi? How to get it? I have a dou phi by dou x. From this, I need to eliminate this dou by dou x and I will have to get a phi. Similarly, I will have to eliminate this dou by dou y, get my phi. And I will have to eliminate this dou by dou z and get my phi. Now, how is this possible? We know that the inverse process of differentiation is integration. Therefore, what we are going to do is, we are going to integrate on both sides. When I integrate on both sides, we do it partially. Why? Because I have a dou operator here. So for the first component, I integrate on both sides partially with respect to which variable? My variable x. When I integrate it, what will happen? I will have y square plus 2xz square, which has to be integrated partially with respect to x. And over here, I integrate dou by dou x of phi. Now this del and dou are going to be inverse of each other and they cancel off, leaving you with the phi. Now what is this phi? Now come on, let us integrate the left hand side partially with respect to x. Y square is a constant, therefore constant on integration leaves you with x. Now plus 2 z square is a constant, x on integration is x square by 2. Plus after integrating, normally we will be adding a constant of integration. Now since this is going to be partial with respect to x, we add a function which is going to be a quantity which is going to be independent of x. Say suppose it is going to be a function of y and z. In a similar way, when I am going to integrate on both sides of the second component with respect to the variable y, what will happen? I have 2xy minus z with respect to y partially, and this is going to be integral dou by dou y of phi. Again we say dou and del, integral and dou cancels off, leaving you with the phi. Now what is our phi from this component? So we have 2 constant, x constant, y on integration is y square by 2 minus z is a constant, on integration we have it as y. And now with respect to y, the constant of integration is a function that is going to not contain y, so it will contain just a mere function of x and z. Now moving on with the last component, what we have in the last component, comparing z. So I am integrating on both sides with respect to partially, here also it is going to be partially. Okay, partially with respect to the variable z. When I integrated, so you have 2x square z minus y plus 2z with respect to dou z is equal to integral dou by dou z of phi. Dou and d cancels off, leaving you with your phi to be equal to, come on, let us integrate this partially with respect to z. With respect to z, 2x square is a constant, z on integration is z square divided by 2 minus y constant, on integration gives you z, plus 2 z on integration is z square divided by 2. Now notice fellows, what we require is only a one single scalar function phi, but what we have been left out over here is going to be three functions phi, a phi here and a phi here. Now I have to combine all these three phi and make it as one single scalar potential phi. How to go about this? What we will be doing over here is, we will be just collecting the terms that are going to be very unique in nature, and when it is going to be repeating one more time, we are going to ignore it because it is just the same scalar viewed in a different way. Okay, so collecting the distinct terms. So I am collecting the distinct terms. So what is my function phi? First term is going to be y square x. Second term, 2 and 2 cancels off, z square x square. Now this is different from of this, so I take it. Now coming to the third term, what is the third term? xy square. But we see that this xy square is already been present, or which we have already considered. Therefore what you will have to do? You will have to ignore this quantity. Ignore. Now coming to the next term, minus yz. Do we have it already here? No. Therefore let us include it, minus yz. Now moving on to the next component. 2 cancels off, x square z square. We already have a x square z square over here. So what we will have to do with this term? We will have to ignore because we collect only distinct term. Now next term, minus yz. Do I have a minus yz? Yes, here I have a yz. So ignore this term also. Now 2 and 2 goes off, z square. Do we have any z square over here? No. So let us include this z square. So plus z square, and combining all the three constants, I can just make it as one constant of integration called as plus c. Therefore what do we think is going to be the required component or the scalar potential? My required scalar potential phi is going to be y square x plus z square x square minus yz plus z square plus c. So this part which I have over here is going to be the required scalar potential for the estimation of the given vector f. I hope you understood. So when you are writing, keep in mind that You will have to collect only distinct terms of f. If it is going to be repeating one more time, please ignore it and just pick all the terms exactly one. So this will help you to define your phi, the scalar potential, in a clear way. Thank you.